let's introduce ourselves first. Start from the recorder.
Hello everyone, welcome to Team 小辣椒南美的语文，阅读履历题，程序谢公题，程序只能巧语，程序黄香柔。
Your name, please.
Hello from China First Senior High School, and our team name is Team F2. My name is Wu Xinyu. He is Chen Yicheng. He is Dan Wenmin. He is Huang Yanming, and he is Chen Zhiren. Thank you for everyone.
Hey, good morning everyone. Team Insight, the bonus. My name is Vincent, the team captain Ray, and then Leo, Howard, and Justin. Thank you.
Our jury members, maybe we start from.
Okay, Chen Junshu from National Tsinghua University. My name is Li Jianhong from Chinese Military Academy. Thank you.
My name is Lamenda from the National Zhongxin University, Taichung.
My name is Chong Ga from Zhongyuan Christian University.
Zheng Gong from Zhongzhen University. Okay, the opponent challenges the reporter, please.
Question number 2, Iris.
Number 2, you have
Reject.
comments. Reject?
Yes.
Question number 8, side by side.
Number 8.
Accept.
Okay, number 8. Okay. Reporter has 5 minutes. And please write your name and for. sentence before your presentation. Okay, please start your presentation. You have 12 minutes.
Hi everyone, I'm the reporter Hong Xiangrong from team 我是小辣椒. Today I'm going to report to you the problem of number 8 semi-sum. And the problem is about investigating and explain a sound of spring listen like a laser shock. And I define a laser shock as like this. And this is my outline. And first I will give an observation and analysis, and I will mention a theory, chart, and sound dispersion, and finally a brief conclusion. And this is my setup. I use a shape to fix a cover, and the cover will connect to the spring, and in the bottom of the spring will connect a rod and I will use another shelf to fix the microphone, which is above the cardboard, and I will use it to record the sound. And first I want to define the pitch, and I will measure the total length of the string, and because the pitch is same, so I change the length, and I will change the length, and I will divide the number of pitch, and I will get the average distance of each pitch. This is the video. And the first is I will release the nail, and the second is the nail will not on the spring, and the third is the specific sound named chirp will appear. And this is my theory. First is chirp, and which means high frequency will turn. It will have two types, and in my experiment, I choose a type of high frequency will turn into low frequency, and it is just similar like this. And the second is sound dispersion. I will discuss it later. And in the diagram, when I knock this point, and the spring will twist two direction, and the behavior of spring first, because it will twisting, and then the twisting will cause the spring to stretch, and the second is diameter of spring will change with time, but it's a little, not very much, just like this. And then this stretch, and the stretch means each pitch will be larger, and I define it to is stretch. And this is the sound dispersion. When the sound dispersion happen, wave will change into high frequency and low frequency. So the wave is similar like this, and because the high frequency will decay with time faster than the low frequency. So after some time, the only exists the low frequency. So the wave will seems like this wave will be, the amplitude will be shorter, and the frequency will be lower. And I use the spectrophone. This is a main I use a spectrogram to see the chirp, and you can see that you can see the frequency will turn high into low, and that is chirp. And in this area, because the chirp will, I define this area is most like chirp, and also, and the vertical axis is frequency, and the horizontal axis is time. And because I cut the chirp into 3 parts, and the first part, I cut to 3 parts, and I use the spectrum to see the peak, and you can see the first peak is 1042 hertz, and the spectrum's vertical axis is dB, and the horizontal axis is frequency. And because it won't relate about time, because it just depends on the frequency. So we can't know the sound changing with time from this graph, and I usually use spectrum to see that. And this is part 2, and you can see that the peak is 1394 hertz, and was a little down, just down a little from than the part 1. And the part 3, you can see that the peak is 840 hertz, and was extremely changed into than the part 2. And I use a parameter pitch, and the large pitch is 1.184 centimeter, and the medium pitch is 1.804 centimeter, and the small pitch is 2.395 centimeter. And you can hear the sound. And this is a sound of the large pitch, and the second is the medium pitch, and the third is small pitch. And you can see the wave that this area is chirp, and you can clearly see the wave will have some. This was very closely, and after some time it will appear a significant wave, and this is a spectrogram of the largest pitch, and you can see the time interval is 0.2 seconds, and the second is a wave of the medium pitch, and you can see the area of the chirp is more, the amplitude is bigger than the larger pitch, and it also shows the bigger wave in this picture. And this is a spectrogram of the medium pitch, and you can see the high frequency is more than the large pitch, and this is small pitch, and you can see the wave is also have the same like the other pitch, and you can see the high frequency is more than the large pitch and the medium pitch, and I use the acoustical generator to improve the chirp is truly turns high frequency into low frequency, and you can hear the sound. It's very similar like our experiment, and this is the wave of the acoustic generator, and because it is only have one frequency, so it's just a little not similar like our experiment wave graph. And this is the result of my experiment. The sidewise sound is high frequency turns into low frequency, and the parameter of pitch except extreme situation, the interval is bigger, the reverberation is smaller, and I use the simulation, and you can hear the sound. It's also similar like the chirp, and in my conclusion, first, the sidewise sound is a sound that changes from high frequency to low frequency because of the chirp. And if the frequency changes from high to low in very short time, it will just heard like the chirp. And the second is the pitch is bigger. Sidewise sound will be difficult to form. And thank you for your attention.
Okay, thank you. The opponent, please question the reporter. 2 minutes.
Okay, so some short questions. First is, I'll do your first. When you define your laser shot sound. Okay, first can I ask you, so when you did your experiment, you used the nail and knocked on the screen, right?
Yeah.
Okay. And for here, when you define it, so you said this is your definition of laser shot sound. So do you use this as a standard for your rest of the experiment?
It's the most standard of my experiment.
So you use this as a standard?
Yeah.
And on your page 24, when you mentioned a short amount of time, like how short is your short amount of time?
In this
Page 24. When you mentioned high frequency to low frequency in a short amount of time.
well,
How short?
shorter than 1 second.
And when you have a diagram for your frequency and amplitude to time, is the label on the time, on the two graphs, is the time axis the same?
Yeah.
Yes. Okay. And that concludes our short questions.
Okay, good. We have 3 minutes before discussion. Okay, then Poland takes the floor.
Okay, so first we want to go back to the problem first. It's tapping a helical spring to make a sound like a laser shot in a sci-fi science fiction movie, and investigate and explain this phenomenon. And in our short questions, we asked how they defined the laser shot, and they said that they used it as a standard for the rest of the experiment that they showed. And in the problem, it said to tap on the helical spring, but they knocked it, and we want to question on whether this can affect the results. And also, for discussion, later on we would like to since they use the sound in the front as a standard for the rest of the experiment, like how do they compare and use this as a standard? And the tapping and knocking, how does that change the experiment? And also that when they knocked it, they knocked somewhere at the middle, somewhere at the top, somewhere at the middle, let's say. So what happens if it tapped on the top or bottom? How does that change? And also the spring mass, because in their models they idealize the spring, where the pitch are the same, and they use the average. But in reality, the spring mass can cause the spring to be denser on the bottom and less dense on the top. So how does this affect compared to what they idealize? And also we want to later ask maybe since they did the experiment and finished, what they think the main cause is for this laser sound, this phenomenon, since we want to investigate and explain. And also for their acoustical generator, when they made the sound, they said, when they showed the graph, they said that unfortunately there was only one frequency. But in their experiment, they said it was a high to low frequency. So if they used a generator and there was only one frequency, then how does that actually recreate their sound? And for their wave change, when they showed their graph at first, for us to make the sound, they made a graph where it was a low frequency to high frequency. But later on, they said the sound was high frequency to low frequency. So why was their results not continuous? And later on, they said they showed a frequency graph to frequency to amplitude graph, and this said that they did not show the time because it did not matter. But then they said that the sound was high to low frequency in a short amount of time. So now it depends on time. So why did it not bend? And we want to ask what kind of parameters in this cause the high to low frequency? And that concludes my conclusion. Okay, so first we want to ask, since you use the sound at the front for your standard, how did you use that to continue on throughout your experiment?
It just heard like the sound I defined, and we can clear hear that is similar as.
So you hear and think it's similar.
No.
And use that as your standard.
I put the video into Audacity and there.
So you compared the shape of the waves.
Yeah.
So how similar how similar does the shape have to be for you to define it as laser shot? Like you compare the shapes. So how similar do you compare it?
The first it was just a lot close together, and then they will just have a shape like another big wave.
So it just has to seem similar. You see it, it's similar, then you think it is.
I compared amplitude and the time, and they are very close.
So, okay, so for some of your experiments, it was 0.2 seconds, right? But you
Yeah.
said your short amount of time is lower than 1 second. So what if you increase that to 1 second? Is that still the same sound?
No, it's.
It's not the same sound, so why did you say it was lower than 1 second? And why did you say
I
it
mean,
was
if
0.2?
we over the 1 second, the sound won't similar to the laser shot sound.
So what if it still looks similar? What if the shape of the wave is still similar at over 1 second? Do you still count that as the same wave since you only look
Sorry,
at the shape?
I adjust my
Okay,
It
now
is,
go on to the next question. In your experiment, you use a nail and knock on the spring.
Yes.
But the problem says to tap on the spring. Does these two ways to make the sound have any difference in your experiment?
Similar, and the tap also will touch the spring and will cause it motion, and I think a knock and the tap won't.
Okay, and since you released the nail,
Yeah.
knock on the spring. So did you control the force you knocked?
I
Did you
control
control it
the
where
force.
it's like maybe you drop it at 90 degrees? Did you control that?
I control that because I release in the same position.
How do you know it's the same position? You're in a
Because
3D
I
environment.
have a cardboard on the spring, and I always let it just a straight line like the
So
cardboard.
straight line. So are you putting it on the cardboard to see that it's in the same place, or do you just put next to the cardboard?
Let's try to see that exactly
So how do you know when you release it, you're hitting at the same point on the spring?
because I just
So you just release it and you don't know if it hits on the same place.
let I hit some
So how do you know if it's on the same place?
because
You have
they
a way
are
to see.
because they are hit in the same position. Because they are just hitting the same position.
Okay, so you think it's in the same. You see that it's in the same place.
Yeah.
Okay. And do you think spring mass? Because in your experiment you used an average, and in your models the pitch lengths are all the same. So, but in reality, the spring mass contributes to the what the spring looks like. It's more dense on the bottom, less dense on the top. So would that cause any? So did you consider that when you were doing your experiment?
I consider that, and I have compared
So what
that.
did that cause? What is the effect of that since you considered it?
They are little different because the sound on the top will bigger, sounds bigger, and the bottom will sound smaller.
Okay. Okay, so then since you consider spring mass, so did you consider about changing the spring shape? Maybe being tilted? Maybe putting it horizontal? Did you consider that?
I put it on horizontal, and in my video I have do that, and the sound will sounds smaller than if I vertical.
And your acoustical generator, when you put out the graph that you, your acoustical generator, when you single out, when you try to make a sound with the acoustical generator,
Yeah.
the graph, can you go to that? Yeah, when you showed, when you showed this, it was amplitude to time, and you said, unfortunately, there was only one frequency. That's what you said. But in your experiment, you said that the sound is high to low
I
frequency.
just want to show the curve is really turns high frequency into low frequency, and I want to show if they are listen to similar. So this is high frequency and into the low frequency, and
Okay, so you said listen similar. So how do you know they sound similar? You just think and okay, so
nothing. They are really changed to high to low.
okay, and so after your experiment, what do you think is the main cause for the sound? What properties?
I think the pitch is the most factor to affect the frequency.
So what about the material for your spring? Do you think that would have any cause?
We tried the plastic, but the plastic is not couldn't generate the semi sound.
Okay. And what do you think? What parameters of the spring is it that is causing the high to low frequency?
I think it's about my theory sound dispersion, and if the sound hit the middle of the spring and will straight into high frequency and low frequency, and that's why high frequency will form.
So what parameters of the spring? What properties of the spring? Like mass, density, length, what causes the high to low frequency?
The pitch and the
Okay. Can you go to your first graph? The first graph that you showed. Keep going down. That one. So you said this. So you think so? This graph is what is representing the high to low frequency.
I just want to let everyone know that is high frequency turned into low frequency, but
in page 7 you said that high to low frequency is being dense into being large. But so according to what you said in page 7, this is a low to high frequency. Page 7. Keep going down. I think you said. And then keep going down. Page 10. Page 10. Oh, that one. Yeah. No, that. Yeah, that one. You said this is a high to low frequency sound dispersion. This one. So according to this one, the picture that you showed before was low to high frequency.
sorry, can you say again?
According to what you showed here,
Yeah.
the picture before was low to high frequency.
No, it's high frequency and low frequency.
And your graphs for amplitude to frequency. Actually, I just wrote that. 18. Yeah, that one. You said, wait, not this. What was this? There was a graph that you made frequencies. That was y-axis was frequency, and the x-axis was frequency, and the y-axis was amplitude. No, this is the time. Okay, and you said that plastic couldn't make a sound, So did you investigate as to why plastic couldn't, why other materials can?
Because the silent sound is because the material of the spring may affect the sound dispersion.
But before you said the main cause for the sound was the length. So why couldn't you just change the length for plastic and why didn't it make the sound?
Sorry, in the same material, the main factor is length and is compared with other
So
different
what properties of plastic caused it to not make a sound?
the material. But in the same spring, the pitch will is a factor to affect the sound.
Okay, time is up for the discussion. Okay, the opponent summarized the discussion. We have 1 minute.
Okay, so first the problem said to tap on the helical spring, and they use the knock, and they think that it's causing the same effect. And when they knocked on the middle and not the top, they think that it does not matter to what the sound makes. And for the main cause that they think is in the same material is what matters is the pitch length. And they think they couldn't explain why plastic use a plastic positive to not make the sound. And for other things like
Okay, time is up. Okay, the reviewer question both the reporter and the opponent, please. You have 3 minutes.
Okay, so the first question is, you said that you use the sound for the standard to compare with the standard.
Yes.
So how to define the both? Yeah.
In relation to
If you use the standard, right? You use the shape wave, right? But you use the wave shape, right?
Yes.
So how to compare both?
the amplitude and the change of time.
Okay. So what about you? You said that she used the standard wave to compare both to find the similarity, right? So what's your answer?
well, I was just asking them because I didn't know why they use that as a standard.
Okay, thank you. Okay, the next question is, have you ever considered the frequency response? That maybe it will affect the experiment result. Okay, fine. How about you? Okay, so the frequency response is that if you put an impulse into acoustic system, the system may amplify a certain frequency.
I think that it will also have affect the sound and but not affect a lot.
Oh, okay. So what about you? Yeah, so it may affect the result, right?
Well, the sound was, well, what we hear would still be the laser sound.
Well, okay. But if you are going to analyze the data, will it change? Will it affect?
Well, the frequency will obviously change.
Well, okay. So thank you. Okay, and well, okay. So the next question is the damping. You use this setup, right?
Yes.
And have you ever considered the damping, which is in one side?
Yes, but we use same spring and so definitely is same.
Oh, okay. So, do you think the damping will really affect this experiment? Damping, yes, just such as if you put your hand in one side of the spring, and it will really affect the
Like, I
result.
think, like for example, if you put maybe fur under it, then it would absorb some of the sound, maybe then plus affecting it. So maybe, I think hand, if you put your hand there, then it will affect.
Okay, so I have another question is, if you put your hand in here and in both sides, what is the difference? I mean, if you put your hand here and you
Okay, I'm afraid time's up. So, the reviewer, you have 2 minutes.
So the problem statement is having a helical spring can make a sound like a laser shock and investigate and explain this phenomenon. Okay, so the main focus is first, what's the description of the so-called sci-fi sound, and second, how do different parameters affect the output sound. Okay, so first, the proposals, they do have a clear video, but they didn't have a clear definition of the phenomenon. And also, they didn't provide the actual photo about the setup. And the theory, they have good approach on the phenomenon, but they are too weak to provide some physical pictures. Yeah. And in their experiment, they didn't have a clear display on the correlating and comparing the data. And at the conclusion, they did not conclude the qualitative results of the experiment. Okay. And this is the opponent's pros and cons. And so they have provided some clear suggestions on the physical analysis and make some point of for the clarification. But I think there are two a lack of their own opinion. Okay. So in the discussion part, the opponent first asked about does the reporter consider two laser shock sound to be similar? And the reporter answer is the shown result in the spectrogram can be compared in the aspect of geometry. And our point is, as a result of depression of sound wave, a clear view for the discussion might be the amplitude, so there's potentially errors. Okay. And the second question is, the opponent asks, why does the wave shape described in the presentation similar even after this time of 1 second? And the reporter answer is, no clear answer from the reporter, but mentioned there's a slight difference. And our point is, it is not clear to define the term a short wire, which is they didn't have even consider the damping and the frequency response. And the third question is, what is the main cause of the phenomenon? And so will the material matters? And the reporter say yes. Okay. So our point is, the reporter's investigation should conduct more experiment on comparing the relevant parameters. Okay. And so this is our additional points. So the first thing is the frequency response, because I think it's a very serious problem for analysis, because it may affect, because if you are going to try to analyze the result, and it may affect a lot. Okay, and the second thing is the parameters. The parameters should be more, yeah, because okay. And the third thing is I think the reports had to have further discussion on the damping conditions. Yeah, because there may be some reflections on the screen. Okay, so yeah, there aren't enough unfixed variables and control variables for the experiment. Okay, and so that's my review. Thank you very much.
Okay, thank you. The concluding remarks of the reporter. Reporter has 2 minutes.
The reason why we use not the tab, because if we choose a tab, we can't show the force of when we tap the spring, we can't show the force, and because they are similar, so I don't think they will affect a lot. And the second is because the main point is to investigate the sci-fi sound. And investigate this phenomena, I don't think we should focus on the more parameters. The damping in my experiment is quite small, so it won't affect a lot about my the sci-fi sound. And the opponent spent less time to discuss my phenomena, focus on my environmental factor control, and the third, we surely pretty picture of our setup. Unfortunately, the reviewer didn't focus on my presentation, and I think the main point of the side-by-side is, in the short time, the frequency will turn high into low, and compare different spring, the material is the main factor, but in the same material spring, the pitch of spring is the main factor to affect the side-by-side. And thank you for your attention.
Thank you. Other question of the jury? Anyone have questions?
Could you go to your slide of spatial break? Okay. So how did you cut up the breaker in that image? Breaker. Okay, you have curve.
Just as the red and the blue means different power. So the red means high power and
Yes,
less.
but I'm asking how do you come up this now? I mean, you see here you still have some red area, and here you have blue area. So how do you come up this now? Or you have some physical intuition of this now?
It's a cosmic curve.
Just draw it by hand.
Yes. Yes, very bad, because I just want to show the
Okay, so there is no like a physical meaning of this curve. Okay. And then it seems you did not mention why the spring has to be elliptical. I mean, in your statement, I mean, at the statement at the beginning of this problem, so they talk about you have helical, helical spring. So in your theory or in your experiment, it seems not should it be necessary. Should it necessarily be elliptical spring? Like for example, if I have a zigzag spring, does it matter in your experiment or in your, because I don't see you mention about the geometry of your spring, right?
It's a little, it's really motion, but it's just motion a little.
So those things will affect your spectral graph. You don't think it will affect the feature a little.
More questions?
I have a question for opponent and the reviewer. You always say that damping, like a friction or reflection. What do you think the result will affect? Such a short observation time.
First of all, the amplitude will probably be lower. I think, like we won't hear it as loud. Maybe first.
I think the major problem is the reflection, because if you damp one side, if you don't damp, there will be a rejection in the spring, and thus there will make some error in the result.
I have another question related to the damping and reflection. So could you go to your slide when you pick the peak in your spectrogram? Okay, so this is the part 1, right? And then maybe go to the next one. Part 2. How do you know that peak, the peak in part 1 corresponds to this peak in part 2? You have a lot of peaks.
Because they are in the same area and
They are in the same area of what? Time? Oh, okay, maybe if you go to part 3. So they are in the same area. That's why you select those. Because, okay, it's around here. Or around this region. But the horizontal axis is the time, right?
no,
Or frequency. Oh, okay. This is the intensity. This is the frequency. But this one should be always changed, right? Because this is the frequency of this beat, right? So your position always change. I mean, if you compare part 1 to part 3, of course you are in different frequency, right? So the position change. So how come you? I mean, go through the same question. How can you pick? How come you determine those are the same signal you want to see?
because I think because compared to the intensity, this is the first big one, so I think we can very
Okay, you want to finish your answer?
we can hurt. Most really hurt it, so I choose this.
Okay, I think because of time, we will stop here.
Okay.
Okay, I'm ready for the grades. Okay, please read the board. Okay, we have 5, 6, 5, and 4 for the recorder. Now we have component. Okay, please. We have 8, 7, 6, 6, and 6. Finally, the reviewer. We have 6, 6, 6, 7, 7. For the grades, anyone would like to give short comment? If no, then we'll have 10 minutes break, and we'll come back in 10 minutes. 2 seconds. The comment on the last 5. Why we have picked some high score or low score. So maybe I should suppose briefly comment on that. For me, I gave a 4 for one team because, in my opinion, this fight, in my opinion, we don't need very deep theory, but just try to get your phenomena and make a model very clear, so audience can know the physics behind. That's my major point for this scoring. We spend too much time on, I cannot say meaningful, but meaningless. That just wastes our time. Just try to dig the inside of the physics. Because some students ask me why some score is low or high. Give some comments on that. the second round, the opponent challenges the reporter, please. So you have to, then they have 1 minute.
Yes.
You have to challenge it, then they have 1 minute.
We're trying to use that 1 minute to discuss that.
But you have to challenge, then they have 1 minute to consider.
Maturity problem number 3, Yonako Sao.
Oh, okay, maybe then you have 1 minute. 他们各有1分钟。Sorry. I thought total 1 minute. Give them some. Reporter, you accept or not? Reject. Reject, okay. Then pick up another 1 minute.
Maturity problem number 7, the loud voice.
Okay, number 7, the reporter has 1 minute. Reject? Okay, choose another one, please. Oh, okay. You have to accept the next challenge. So you have no choice. You know that. Just pick up anyone. They have to accept.
Okay. We would like to challenge the problem number 6, American balls.
Okay. They have to accept. So it's number 6. Okay, reporter, number 6. Okay, please write your names on the board.
present to you breaking balls. So first is a problem. Two steel balls that are joined together can be spun at incredibly high speed frequency by first spinning them by hand and then blowing on them through a tube. Example is a drinking straw, and investigate this phenomenon. And later on we'll be using Lagrange equation. And so first is our experiment setup. Our equipment is steel balls, drinking straw, multi-part adhesives, steel plate, and camera. And we stick them together like this. This is our setup, like this. And we also use a lamp for lights to help us take the video. And this is our setup like that. And next is what we observe. Now this is what we take under a high-speed camera. And what we observed is that it is pure rolling, and we don't. And the drinking straw to the side is not that we are blowing it. It's just that because it's taken through a high-speed camera, it takes time for us to take the straw out of the scene. What we use as in our experiment is we blow it to an incredibly high speed so that we cannot increase it anymore, and then we take the video of it slowing down. Because what we observed is that speeding up and slowing down, it is symmetrical, but when we are blowing it, it is unstable and it moves around. So when it is slowing down, it is stable and staying at one point, and that is when we take the videos. And next is our theory for this phenomenon. I know it's a bit hard to look at it first, and I'll explain what each of them means. First, it is like this, and we spin it by hand, and both at the point A and B, it gives it a way to spin, and when it starts spinning at a high speed, it goes up. And then we use Lagrangian, and the definition is the Lagrange equals the kinetic energy minus the potential energy. And when we write each of it, we can open it like that. And the I is the rotating inertia. The psi is over here. The spin, the amount of degree it spins here, the speed. And the psi is here, where it spins. And that is what we open it as. And because we use two of the same steel balls, we use the M is the same. And then we calculate it. We can calculate the rotating inertia of 1, 2, and 3. And because the velocity at the point of contact is 0 when it is pure rolling, and because it is pure rolling, the speed, the psi dot and the psi dot is the same, and we can get this equation over here. And then because through this we can know that the ball feels slow, so the sine dot is close to 0. And then because the psi dot and psi dot is the same, we define it as omega. And then the new equation is seen here. And then after we partial it by sine dot and then differentiate it by time, after calculation we can get that when we partial Lagrange by sine, it equals 0. And our theory, and after simplifying it, our theory is that the theta here is 2/5 minus the g over r omega to the power of 2. And then this condition is, their condition for this theory is that it is pure rolling and there is no displacement as we observed. And the things we neglected are the air drag and our experiment. This is we use two different kind of balls, which is small ball and big ball, where the R is 0.5 centimeters, mass is 14.1 grams, and the big ball R is 0.8 centimeters, and the mass is 33.4 grams. And the red line is our theory, the black line is what we get, and the y-axis is cosine theta, the x-axis is the omega to the power of -2, as seen in our theory here. The two things are what we use. And this is our result for the small ball, and this is our result for the big ball. Now our conclusion for this thing. First, according to our theory, the cosine theta is 2/5 minus g over r omega to the power of 2. So our theory is that the red line goes over this point, and our result, as you can see, is very similar to what we think it is. So the reason for it being slightly less, we think the reason for error is because of the thickness of the glue. Because when we calculate in our theory, we use the R for the ball, but then the thickness of the glue in between the ball increases the R by a tiny bit, and that is what lowers the value from 2/5. And because our experiment result, what we observed is that it is pure rolling, so we conclude that friction has no big effect in our experiment. That is why we did not include it in our equations. And when it is rolling fast, what we concluded is that cosine theta is close to 2/5 when it is rolling fast. And that concludes our presentation.
Okay, thank you.
Okay, so firstly, pertaining to the problem statement, what do you think the action as stated in the problem statement as drawing it by spinning it by hand and drawing it by an air tube as you do the phenomenon? Yes. Do you think why with this problem statement that you have to use your hands to spin it? Do you think there is any correlation between the action of your hand and phenomenon?
Well, just start spinning it.
Okay,
You just have to start spinning it, because what we observe, what we use for our experiment is slowing down. So the starting of it doesn't really matter for us.
Okay,
we just start spinning
so right there, and we'll begin to the next one. And how about the air tube? What do you think the role of the air tube actually acting the phenomenon? It's just accelerating it, just simply accelerating it, no other side effects of it.
No, it also contributes to how the ball starts tilting up. Because if you only roll it, it's just spinning on the plate. It gives it another force.
The air tube actually gives it enough force to tilt up.
The starting force for it to tilt up. Once you start tilting it by a tiny bit, the force itself, the torque weight in it starts acting itself, and it stays in the point where it's tilted up.
Okay, so I think I'll hold that for the discussion. Okay, so now you mentioned that actually the thickness of the glue would potentially affect the error, right?
At least in our
So according to the problem statement, they say the two steel balls are joined together, but they did not say they are joined together on the surface. Have you considered that? Maybe the steel balls are held together in a constant distance. Or like, for example, allow me to bring one of the model. So this is like the prototype of your kind of experiment. So if you consider the type like that, there is actually a slight difference between them. So that will potentially actually explain your errors or actually the phenomenon.
Well, because our experiment is only where it is
for the question.
Okay, thank you.
Okay, the opponent has 3 minutes before discussion.
Okay, go ahead. So on number 3 and for the commentators, I'm going to give the opposing experimenting variable, and now I'm firstly going to take a view at the problem segment. So firstly, two steel balls that are joined together can be spun at an incredibly high frequency. By first spinning them by hand and blowing them through a tube, for example, a drinking straw or whatever. It explains and investigate this phenomenon. So according to problem statement, we can actually derive two main focus on this. Okay. What is so special about the case of high frequency? So what has to do with another term, low frequency? What's the difference and what is the condition that hold this phenomenon? And secondly, what are the purposes of the two-step of spinning them by hand blowing respectively? Because if it actually means nothing, then it means that there's actually not such physical meaning for it to put on its current statement. So firstly, we'll go on an overview of the reporter's presentation. So firstly, in a step up, actually, well, they have given us a lot of introduction on what the phenomenon is, but they actually did not give us a clear example of how you guys managing with the variables that you use and what kind of method you use as your analysis. And in the observation video, they clearly provide a video for our understanding. And then in the theory part, they have given us a simple theory picture with actually there's no citation, I suppose. And there's several counts, like there's no reason for there any further description on ignoring the air resistance and the force and about the experiment, they have not mentioned about the effect of the airflow is perhaps one of the parameters they should conduct, and their lack of parameter. Yes, while we previously say about the hard distance between the balls, and they do that data because it seems that in their graph there's only 5,000 for these experiments. And conclusion, which it could be a further suggestion for the reporter to do some explanation on the possible errors or further discussions. So firstly, could I go to the discussion part? Yeah, go ahead and proceed. So firstly, just like coming back to it. So could you give me an short description on what's the physical meaning of using the Lagrangian mechanism?
Simply a tool of physics that we use to explain this phenomenon.
Okay, so then there will be tricky. So and later about the you mentioned about the precession in the first part of
I didn't
your,
mention.
you can turn to your maybe next page or director. And next one. And the next one. There actually was a word.
That was an error.
Okay. So let's firstly talk about the effects of using your hand and blowing on the air. Because the opponent thinks that actually while you're spinning them, spinning the balls by your head, well, you know, our heads are actually in perfect status for the action. So which means while we're trying to spin a ball, we're actually creating a net force on the centroid. If you know what I mean. So actually, other than the rotation on the z-axis that we originally expected, it surely becomes slipping all over the world, all over the platform you use, right? You're not going to spin right here. You're going to slip for. So do you think this might affect your phenomenon or cause?
Right. So for our experiment, it wouldn't affect our experiment because what we use is when it's slowing down, when it's staying at one point, when it's stable. So because we think there are, so we simplify the experiment. We don't want that effect to have it in our experiment.
So do you think this possibly the reason why the ball tipped? Because as we know that the friction force given to the contact point is actually a relative.
We don't really think that would be.
It's the opposite way of the relative speed.
No, we don't think that when you spin and it moves, we don't think that would have really a big effect on the tilting because for us, our steel plate was small enough that we have to control our spinning to have it stay one point, and then we blow. So that's
the main cause of the lift. Do you have any?
Well, when you asked in the short questions, we said it was caused by the blowing.
The blowing. So you could draw a similar for us on the blackboard. So what do you think that caused the lifting?
the torque weight.
In the torque.
Torque weight of the contact on A and B.
Okay. So let's go to the next one. So what do you think is the main focus on the condition why the balls could acquire such a high frequency? So what's the difference between like one ball? What's the difference between you're using a system with two balls or one balls, and why in the two balls we could actually acquire this kind of frequency? Like we're not like sticking a wing to a top and going into spin back faster than it.
Because when you put the two ball, there's a torque weight on the side when you blow.
Yes.
Yeah. And so that is how it affects.
So you think the torque actually provides the condition for the high frequency? Because in the opponent's opinion, it's actually because of the tilt of the balls, which actually provides, it's allowed to obtain the pure rolling, right? So when in the pure rolling, it makes
So the pure rolling is just because the side of the side.
yes, but also because the pure rolling, the contact, the relative velocity of the contact point between the ball and the floor becomes to zero. So whereas it means that you can actually tell that there's no friction working on it. It's not less friction, it's actually no friction working on it. So which provides the balls to actually spin while accelerating it through an air tube, but also you have actually no or very, very less friction the friction effects on the ball. Do you agree with that?
Well, we did say the friction is nearly zero in our conclusion.
Oh yes. All right. So. So, well, like basically, we actually think that all the friction we expect does actually plays a major role in the phenomenon in describing it. So, have you tried any other theoretical approach on trying to constructing a model of it other than the Lagrangian?
Maybe I can answer what you asked in the short question when you add a stick in the middle. Maybe.
Yes.
First the I1 and I2. When you increase it, first of all the I1 and I2, which is the rotating inertia of this point and the point inside going in, it would change. The rotating inertia would change, and the relation between the side dot and the side dot would also change, and causing at our conclusion the cosine theta, the max would be different. It would not be 2/5. It would be less.
Yeah, so I suppose by my opinion, so actually, because since that not only this component and this component has a lot of stuff associated with the moment of inertia, right? So it will be actually a various reconstruction of the structure of the equation. Do you believe that? If there is a tiny difference of the thickness of the glue or a constant
so we can just go back.
So
So we can just go back and take it back into our equation.
So do you think it will affect the construction a lot? Because I consider
Like,
that it's
how can you
actually
define
a
the
ratio of it. It's a multiplication other than a simply error. Because you can see, just for example, as you can see here. So if there is a constant distance between the two steel balls, we could actually tell that this is not going to be equal. This actually to be a multiplication of the ratio between the half length of it and the radius of the ball. So there actually means that in your next conclusion, there will be even a multiplication between all your data analysis. So could you try to indicate us your data? Is there any data on the relation of the theta and the rotation speed? We have that one graph. Okay, so we have this one here. So apparently there are, but just for example, according to the graph. So could you like explain why it's started here, or just experimental error?
Experimental error. Oh, and I just suddenly thought of it. You said that we didn't mention how we analyze and measure.
Yeah, it's like
we did it through trackers.
Oh, you didn't do tracker?
We did it through tracker.
Oh, this is tracking. So, like, meaning it's actually a great thing if you measure the field of angle on the side camera. But how do you measure the rotating speed and spin velocity respectively?
Well, I know they did. I know my teammates did it through tracker frame by frame, they did everything.
Because I believe if you only analyze it through sideways, it's going to definitely give some deviation of your calculations. Alright. So maybe we go back to another one. Okay, so actually let me get to my paper here. Where's me? So so the actual here.
Okay, so on how we measure the turning speed.
Yes, the rotation.
Rotational speed, because because when we said it is stable, staying at 1 point, still rolling, and our camera is also staying at 1 point. So what we is having a y-axis, x-axis on the tracker, and we see when it goes back to the same point, from 1 point, turn one circle and back to the same point. That is how we measure it. We track it because it goes through frame by frame.
Okay, so that's great. And like pertaining to the pertaining to the experiment itself, do you think that so mainly your investigation is focused on the steady state, right? On the steady state of the motion of the ball. So is this just an hypothetical question? Have you conducted any theoretical model, any theoretical attempt on describing the non-steady state, such as the accelerating, which is non-stable through while you're going to, or the decay of it?
Because like I said when I was presenting, we said that what we observed was that accelerating and decelerating, it is symmetrical if you can control the acceleration and deceleration, but because we cannot control the acceleration to where a equals a constant, so we do not use the acceleration, which is why we use the deceleration, because it is stable, we can control it.
It's very stable than how
Stable.
Okay. So next one, you say that you use a steel plate to place the experiment, right? So have you considered that the materials affect on the phenomenon? Do you think there's any possibility of it could affect like such as the angle, the rotational speed, of course, according to friction? Do you think it has any kind of role that's dominant to this phenomenon?
Well, as you can see in our equation, there is no part where the friction does not contribute to the equation. So what we think is that as long as the place where we place the steel ball are smooth, if you don't put it on maybe carpet, then it shouldn't affect that much.
It should affect, or it
Should not affect that much.
So because I think like if it's not perhaps pertaining to the main phenomenon, but it could actually act as such as a stabilizer of your pure rolling motion, perhaps. So next one. So actually we think that
Okay, please summarize the discussion.
So throughout the presentation, we've seen that the reporter gave us a stable model to as the brainy mechanism to describe the motion of the ball, which indicating the effect of hands and the air tube blowing, and has actually no considered non-human experiment to support the idea, but and other than relevant parameters. But the opponent still thinks that actually in the problem statement, the hands effects are pretty dominant and the air are pretty dominant to the mechanism of why the balls are lifting to the ground. And secondly, the blowing air tube actually does a lot of effects, while the force of turning such as something has to do with fluid dynamics. And other than that, the opponent believes that there is one further suggestion for the reporters to conduct more investigation on the relevant parameters of the setup, and give them give us a further more accurate methods on how they conduct the experiment and further how they explain the motion. And other than that, we believe that there's still a lot of condition they have not considered and they're ignoring too much in their investigation. Thank you.
Okay, the reviewer. Questions also.
Okay, I have some questions to the members. Why you will fall down to some work or outside experiments?
Right, so first, when we're doing experiment, we would not have outside disturbances.
No?
Like
Any-
when we're doing an experiment, we make sure that there is no outside disturbances next to.
No gravity?
Well, there is gravity because you can see that in our equation it was 2/5 minus g over r omega to the power 2. So there is
Okay.
gravity in
Can
this.
you turn to your photo? Okay. Did you calculate your from crater?
Yeah, we calculated it ourselves. All we got from paper was like one.
So why you will tell a brief explanation, please?
Right, what's up?
Brief
Yeah, the
explanation.
shortcut of A and B, and once they are on level, they will start going to 1 point.
In this picture, I see there is a self-revolution, right? Do you consider that?
Yeah.
So you draw on the web or free-body diagram before you mention that for rolling condition.
That's really
Okay. Turn to your page 6. Okay, you mentioned that the motion is for rolling. How do you show?
well, we can set up camera and look at it through tracker, and since the camera does not move,
You
there's a
look at
y-axis
You
and
look
y.
at the video and you think it's for rolling.
No, we put this video here, but we already put it through tracker, and we see that it does not move on the x-axis. Just put a certain point because the camera does not move.
What about the condition before rolling?
You mean transition before pure roll?
You mean that you just rotate it in the beginning, you just for rolling?
No, because this is the deceleration. We already accelerated up to the point where it's stable, and this is the deceleration.
So I asked what kind of condition before it's stable,
What kind of condition are you asking for?
before for rolling?
Like what kind? What do you mean condition before pure roll?
Just start the spin.
So start the spin. Well, spinning by hand.
Yes.
So
Spin by hand and then what phenomenon
what kind of phenomenon do you want?
before for rolling?
Like it's rolling. What kind of phenomenon are you asking
Your
for?
meaning is it rotates in the beginning. It
Okay, time is up for the question. Okay, reviewer has 2 minutes to take care. please take the floor. 4 minutes.
Greetings everyone, I'm Chairman of Team 我是小赖的 from National Provider Stable History. I'm going to review the problem, and the problem is talk about investigating the motion of two steel balls joined together and spun by hand at first and then blowing on them through two. This is overview of the reporter, and I think it's lack of definition of the rotating speed. It does mention it, but problem statement mentioned. And the slow motion video is detailed, and theory use some Lagrangian equation. It's most more, but I can't know it clearly. And he had lack of parameters. He only used big balls and small balls, but not explainable about the effect between them. And not modeling and result, he used the equation and said it's going fast, but I don't know how fast. And just show the result in conclusion. For opponent, I think he understands the report almostly, and comments for reporter I think is accurate. And discussion point partially relevant, but some misinterpretation. Of the discussed questions, spend less time analyzing the phenomenon. Time management, I think he's doing great. It's about missing point, because in his presentation shows the self-revolution, but not discuss of the revolution axis between them. Other affect the result, because he doesn't mention any another factor. And definition of paralleling doesn't explain well. And because only the only contact point is between the table and with the ball, but in conclusion he said no frictions effect. I don't know why. And I also see that in her setup use abrasive surface, but he said no friction. And the important statement mentioned the incredibly high speed, but he didn't measure. So I don't know why, because this is important. Especially I consider the spin angular speed is very important, because due to the spin angular friction force and self-revolution and revolution friction force, they form some torque, but they didn't discuss it. And I don't know whether the condition is correct in counterclockwise or clockwise. Both will be appropriate. And I guess that the formula and some pictures not from himself. And the opponent talk about blowing air effect, but he doesn't mention so what is the effect. And he also showed a model, but the same, no explanation. And I want to know the biggest speed and angle of the phenomenon. Thanks.
Okay, thank you. Okay, the concluding remarks of the report, 2 minutes.
Okay, so first I want to refute about, further explanation about the missing points that the reviewer put out. First is the definition of pure rolling. We did do a definition for this. It was where the psi dot and the psi dot equals to the same. That is when the pure rolling happened. And for the frictions rolling experiment, because in our experiment what we measured is the deceleration. So what we said is that in the deceleration part there is no effect for the friction. So the friction rolling experiment is at the start where how the ball starts to have the tilt. That is related with the hand and air blow, and also the hand and air blow, because when you spin it at the start, there's at one point where there's one of the ball where is the point, and the other ball starts sliding. And with that slide, it gives an angular momentum, and that is how it starts lifting up. So friction is affected at the start of the experiment. It affects the amount of time that it takes to tilt up. And for the distance between ball that the opponent put out, it affects the rotating inertia, the I1 and I2, which is the axis on the top and the axis into the board. That is those two rotating inertia is where it affects. And our theory, when we said what we calculated, is just that most of the part where you can see that there is calculation is what we did, but the start and the end is what we got from the reference. But when they asked, we were on the theory page, which is most of the calculations. And they said that we didn't mention the axis, but in our picture, while we were explaining the theory, there were clear points of the axis that we showed. And that concludes our remarks. Thank you.
Thank you. Okay, the question is Julie.
I have a question for a reporter. So you talk about your theory comes from a reference, right? So because you don't, or you only did a few experiments, what's your own contribution in this problem? For example, you copy the theory from paper, right? Because I find there's a published paper in 2015. You have exactly the same image, exactly the same coordinate system, and of course they use Lagrangian. And okay, so I assume you just copy that, the theory part. So then I'm wondering, because you only have just a little experiment. So I would like to ask, what's your own contribution in this problem?
We did some experiments, not that much though, but we did some experiments, and we verified for ourselves that in reality it fits the theory.
Last question. Okay, I want to make sure in this formula, okay, cosine theta, okay, the capital omega is the same, the equation you derived before the lowercase omega, right? You say here you use the omega. So what the difference between the capital case omega and the lowercase omega?
Well, it's just that for the cosine dot and the phi dot is what we define it as omega for later on, because
So
they are the same.
both of them are the angular moment, angular velocity, right? Okay, and the next page. Okay, so it means in this formula, it means suppose the velocity is stable. So the cosine theta means the tilde angle.
The theta is here.
Oh. So suppose it's stable, so we the cosine theta. Thank you.
I have a question for the reviewer. You say the theory is clear for the proposal, and your comment is very clear. So do you understand?
Because I also did my experimental problem, and I consider it's not because of it. And we also read paper, but I think the situation is not in counterclockwise or clockwise. We have some another experiment.
Maybe let me start with the opponent. Why the title of the question is hurricane falls?
Why is the title
Yeah,
hurricane?
any clue from that?
It is spinning as fast as a
Just
hurricane.
very short, brief answer.
You mean the phenomenon or the problem?
Yeah, the problem was.
Because well, we're associating this kind of sequence of action to the ball, to steel balls as our construction of the experiment. We could actually observe a very high frequency or very high rotational speed of the balls. I think that is why, because we know as our understanding about hurricane is object is very spinning very fast.
So the major major motion of the ball is what?
So I believe that the jury is trying to ask about the effect
No,
of
we
the air.
just try to get a simple picture of this problem instead of working on the Lagrangian. It's good, but we should try to get a simple picture and get a
So
model.
like
of
we
that.
have we have several theoretical
And
tests on
from the
problem.
title, maybe we can get a simple model for this problem.
Yes, we've done through attempts through as well precession, but actually the precession model could only provide us a stable model of it. So later I consider that there is another potential to do it with energy.
Maybe you come up with that. Just try to get a simple model of this problem. So why the two balls will choose the rotation instead of other motion? Why it stands up? Why it becomes like hurricane?
About hurricane also title, I think it's because of I agree with the reporter. Incurable steady motion, no friction, so it was written so fast.
How about you?
Simple model. So hurricane balls. So hurricane, it's probably just it means it's twirling. There is a speed of twirling. Probably high speed.
When you try to use the hand in the beginning, rotate, but I guess it suddenly will stand up, right?
Yeah.
The ball. Why is that?
Why it stands up?
Yeah. Then we can model this. Then it becomes just rotation is mainly rotation.
So when we spin it by hand at the start, because it's not stable, it moves around, and then at some point there's a friction where it affects at least one of the point A and B, and so then there is a angular motion of where the point of spinning is at A or B, so it spins like that, and there's an angular motion, and it starts going up.
Okay, I guess we don't have much time for further discussion. Review. Raise your board, please. 4, 6, 5, 7, 5. Okay, do you remember? Well, you could give some comments on the grades.
Yeah, maybe I can give it.
High school. Low.
Actually, at the beginning I gave you 5, but when you try to answer the question of jury, it's not get the point. So.
Okay. All right. Thanks. So we're going to have 10 minutes break. Okay. The opponent, please challenge the reporter. 1 minute. Push. Number 2. Okay, number 2. Reporter number 2.
Only the white stand.
Sorry, you have to pick up one there.
Looking manual.
14, number 14. Number 14, right? What's number? Number 14. What's the number?
We accept.
Accept. Number 14. Now please write your names on board.
presentation the report.
So on number 3, and for the computers, I'm Mark from Team PF2, and today I'm going to present you the problem number 14, looping pendulum. So firstly, it's the outline of our presentation. So first we'll begin with our introduction and observation as theory, and which followed by our experiment, and that is our conclusion. So firstly, here is our problem statement: connecting two loads, one heavy and one light, with a string over a horizontal rod, and lift up the heavy load by pulling down the light one. Release the light load, and it will sweep around the rod, keeping the heavy load from falling to the ground. Investigate the phenomenon. So the key point we could derive from this problem statement firstly is what does the motion of the light load have to do with the heavy load? Which is what is the correlation of their motion, and what are the trajectory of the two loads respectively, which we will use as our analysis of the motion. So next is the observation video we would like to show you. So first you can see there's obviously I'm sorry about it. So firstly you can see my hands holding a releasing gadget we use to release the light load, and it's dropped horizontally, which the direction of gravity is actually upward. So and you can see the velocity of heavy load actually accelerate at the first part, decelerate at the last part, and which comes up to a stop. And so next part is our theory. So firstly, I would like to introduce our variables here. So firstly is the 2r, which is the radius, which is the diameter of the rod that we use as our horizontal rod. And next is the L, which is our initial length of the cutter strand from the top of the rod to the light load, and where the X is the difference between the position of the light load from the starting point, which means at the very first initial process, the X is equals to 0. Okay, that's how we define our variables here. And notably, the phi is the initial angle of our motion, and theta is the round of the string that coiled of the rod. As we know that while the light load is spinning, is rotating around the rod, the cutter string is beginning to coiling on the rod. So to further keep another physical meanings of the motion. So firstly, I would like to use the force diagram analysis to keep an introduction on what actually happens in the motion. So you can see here as the rod and the light load and the heavy load. So there will be a tension that's pulling the light load this way, and the gravitational force for the light load and heavy load, and the tension on the heavy load over here, and which is we define our coordinate in this sideway. So when we zoom into this part, we can see that actually, while in this process, we can see that there's actually a difference between the tension of these two loads. So in order to calculate, we have to derive all the friction that's involved in this process. So therefore, we use the Kaplan equation where we could derive from the calculus method, which we firstly calculate the overall force of it, and use the trigonometry to describe what the force actually works on the rod, and then through the method of calculus, we can derive that the relationship between the two frictions could actually be expressed in this form, which has an multiplication of exponential of the mu, which is a coefficient of friction, times theta. And in the next part, we could actually, by analyzing the force working on the light load and heavy load, which is allow us to do further calculation if we does really need to use the computer to simulate all of the other situations. And notably, we can see the relative length here could help us to, such as calculate while the light load is rotating around the rod, we can calculate the centripetal force of it, or the criterion of the heavy load to start accelerating, which we derived previously. And here's our experiment. So firstly is our experimental setup, where we have the horizontal rod here, the cutter thread here, and the support here, well, it's behind and okay, so firstly I would like to introduce our releasing gadget. So in order to prevent that using your hands releasing the light load would potentially affect the phenomenon, so we use an electromagnetic along with this electrical supply switch, which in the very first process, my classmate would hold the electromagnetic, and after we turn on the switch, we put out the magnetic force out of our consideration, and the light load would fall along to its own trajectory, which would give us a less error of it. So here are some preliminary experiment on determining what is the actual value of the friction. So we use our classical meter here. So according to let's relation we derived earlier, we could actually calculate our mu k, which is our kinetic friction force, kinetic friction in this form. Well, and this is our graph here. So and next is give and take 1 standard deviation. So let's talk about the trajectory of the light load and heavy load respectively. So as you can see here, the blue lines is the trajectory of the heavy load's y coordinate. So you can see basically at the very start of the motion, the heavy load begin to accelerate downward, and thereafter, while the rotation of the light load occurs, it starts to accelerate and then bounce back in the first part of the stopping point. And you can see as the time goes by, and you can actually observe that the radius of the rotation of the light load is getting smaller according to this graph, and it's including the x-axis and the y-axis. So when it first jumps downward, it's pulled horizontally and does vertical circular motion, which we call VCM, with gradually smaller radius after the stopping point. And as for the heavy load, it drops down initially and reaches the lowest point and then bounces back. And then thereafter stays stationary. So okay, so as for the parameter for this graph, we got a mass ratio of 14:1, and the length of the initial straight is 0.75 meters, and the initial angle is 90 degrees angle. Okay, sorry. Analysis of motion. So this is another analysis of the motion of the heavy load and the light load. There's another typo here, I'm sorry. And you can see there's another typical weight of this part, which represents the velocity position of the heavy load, and which this is the angular velocity of the light load, which is describing its rotation around the rod. So this is another, it's the same, okay. So, well, we can see that there's actually a critical point, quite obvious here, which makes the velocity of the light load actually bounce back up, actually goes faster, and actually, and the theta of the light load, it actually has formed another cyclic motion here. And this is one of the trajectory of the light load in as a whole motion. So we can see that almost in the delta R, the decrease of rotation radius is consistent in every cycle, which is almost like a Archimedean spiral. So we discussed the motion on different mass, like different mass ratio, which we think could potentially like affect the phenomenon. So you can see here is like as the mass ratio decreases, so from this one to this one, the falling time of heavy load also decreases, which means it's a slower motion of trying to explain of the phenomenon we're trying to explain, and resulting in less rotation of the light load according to the time as well. And well, you can see tell as we further as our previous analysis on the acceleration of the heavy load depending on the mg, depending on the gravitational force and tension, we could tell that the heavy load is, and it will longer it will fall further shortening there, and which is our previous prediction of it. So well, so let's begin to another part which we discussed. We discussed a motion of load under a lower mass ratio, like to which we really see, say the lowest is 1 to 7, and how would happen if we done like 1 to 4, 1 to 3, or more less, or less. So as you can see here is another opposite video, and which you can see there's actually a second dropping there. There's there's two processes which act as a second drop. It's actually because that while we're lowering the mass ratio to 1.3 as in this experiment, we actually could observe a second drop. So what's really, so this is a typical graph of the motion of the mass ratio under 1.3, 1 to 3. So what actually matters, what actually happens is the mass ratio is while the light load is trying to rotate and stop the heavy load from falling, you can see here, but actually the mass ratio is not enough to increase the tension that allows the light load to acquire the enough condition for the stopping point at the first round. So it's actually that's the motion stop for a while and then occur a second time, which allows the heavy load to drop twice. So this is another instance that's comparing to the previous graph that we've shown. You can see there's obviously two significant drop in the graph. So two stages of the heavy load downward acceleration we can observe here. So explanation of this doublet side is actually as the centrifugal force from light load increases, the force of the heavy load accelerates, which is in association with the tensions inside the motion. And when light load stops dropping, the system coefficient switches from the static to the kinetic one, kinetic to static one, which it depends on the way we discuss it. And when the tension is between this certain range, we know that heavier is stationary, which is according to the Capstan equation, which we derived before. And if the minimum of T1 is smaller than this, which we could get here, those heavy load will drop again, which is why we call this stop and slide. So even what if we even go to a more even lower mass ratio? It's what would actually happen is it would actually fail to rotate or like just bounce back together. And so while we're lowering the mass ratio to 1 to 2, it actually fails to complete the full rotation, and as it's too long to complete the rotation, which is associated with the angular velocity. So we can see here is the discussion of different loads of the the rotations and the accelerations, and the last part is with different phi is different angles. So you can see there's actually a significant of the slope here, and larger initial phi becomes a centrifugal force. And that is our summary of discovery, which we say about the BCM, the mass ratio, the critical mass ratio, the length, and there's certainly also critical criteria of the initial ratio and the time angle.
Time's up. Thank you.
Okay.
Component 6 floor.
Okay, recorder, please turn to page 19. Yes, and I want to know the physical meaning of this. I don't know what this meaning in this experiment.
Okay, so I can explain it as like, well, in the first class we mentioned about the equation called Capstan equation, right?
Yes.
So what's the Capstan equation meaning is actually we're trying to calculate what's the friction on a rod. Well, you know, the friction is not as simple as we're doing it on a planetary surface. So what we can see is like we calculate the normal force here, and we using our calculus method, we could actually calculate the friction, what is on the rod, what is actually working on the rod. So this equation is actually telling us that what is the difference between the tension while working in the motion.
Okay, I know. And you have mentioned you are calculating your friction working in this experiment, right?
You mean this one?
Yes. So could you show me the diagram of how you calculate the friction with time passing by? I want to know with time passing by the relationship of the friction.
Oh, okay,
How is the friction working?
well, as we know that according to the material, so we know that the coefficient of friction is actually a constant throughout the time. But what actually matters is the theta. Is I previously said that while the light load is rotating around the rod, so you can see the concentrates is actually like rolling and coiling on the rod, which means one turn, second round, and 3 or more, which actually form a greater friction since this exponential component.
Okay, time is up for the question. So you have 3 minutes before the following discussion.
not definition of clear setup because they included electromagnetic generator, but in their setup picture, I couldn't see it. So I think the setup picture is not clear at all. And in their analysis, including the free body diagram and capacitance equation and trajectory of light and heavy load, I think they do clear analysis in this part. And in their experiment, I think they have not compared the result and the theory because they use very abundant equation to explain how the friction works. And I think they have to calculate the theoretical value of their friction force and make a gram of it. Or by doing so, I will have a clear understanding of their friction force or decreasing or increase. And in their conclusion, have low mass ratio will cause the twice drops. And this is the discussion I want to make. I want to know whether the string mass will affect the result because they have not definition of their string mass. So I'm not sure whether their experiment is in ideal condition or not, or another one. And will they have other force factor in this experiment because they have mentioned the friction force and the tension of the string. But I want to know more about the factor that will affect the result. And because the light law are passing by, because they are light, so the air resistance may play an important role in this motion. So I think they have to make the air resistance in their important condition. And they have calculated the maximum of the mass ratio. As if they have the minimum, and it should have a maximum, and we will know the range between the maximum and the minimum between the experiment. And I want to know the string properties because I'm not sure whether the string is flexible or not because they may affect the result too. Because if the string is flexible in their release, in their process of the releasing, maybe the string will getting curved or have another result due with that.
You have to move to the discussion with
okay.
the reporters.
And I want to start the discussion. So whether you have considered the string mass.
No, because according to compare the mass of the light load and the mass of the head load, it's actually pretty minor, like 100 to 1 compared to the mass ratio. So we think it is actually negligible in this process because of the mass ratio of the light load and the heavy load compared to the spring.
Okay, but could you turn to your free body diagram? Yes, in the friction one.
Oh, the friction.
Yes, thank you. But if you didn't consider the string mass, would you think the friction will be equal? The two sides friction will be equal, and maybe the light load can rotate.
I think there must be a significant difference between them because since the normal force is actually given by the tension of the light load and heavy load is given in the motion. So I think it will not significantly affect us.
And I want to know what your meaning of normal force? I want to know this.
Oh, the normal force is, well, we considering the force here, the tension here, and the tension this way. The normal force is actually the force that is perpendicular to the surface on every single point. Like okay, so N is actually the force while you're applying this in this direction.
Can you draw this?
Okay,
Because
so-
I can understand it at all.
So just considering this is the rod that we use as a horizontal one, and this one, these two, which is slightly different. Okay, so this is P1 and this is P2, which is equal to P1 plus P2. So just accept this. So the normal force will well considering this area, or like this theta. So the normal force would be this very single force that is in this way, which is perpendicular to this tangent line.
Don't you think the strength mass will add additional press to the rod, and maybe we'll have a normal force that comes up?
We think that actually, well, we're using this string is actually, I remember it's like 3 to 5 grams, and while this goes are like 40 or 140, like this one is 140 in grams, and
So you think in the comparison, so the strength mass is little.
yes, very, very,
So
very
you
light.
think that can ignore it?
Yes, because compared to these numbers, it's actually very, very small.
Okay. And please turn to page 17. And I want to know why the theta will
Oh, this is
suddenly-
typo. This is the light load. This is not the
Oh,
light load. I'm
okay.
sorry, it's a
Thank
typo
you.
here because after we produce this picture, we failed to
I want to
edit
know
it.
why the theta will suddenly comes up.
Because something comes up is because the acceleration given by the maybe I can show you here. So as for our experiment with suppose the light load is actually placed on here, right?
Yes?
So while the gravitational force is working this way, which in this part of the motion is accelerates the most. So at the very first part, we can see the actual theta, which is well, I just call this one theta. So it's actually moved the fastest. So you can, along with that, you can observe there's one significant acceleration in the first part of the evolution process.
So you have released the line in the same angle.
Yes, we've also compared them to, well, with different, sorry, I will repeat, display, a different initial angle, and which was shown that with greater, you can observe this acceleration here. Yes.
The same angle.
The same angle will give the same.
The gap is the same.
Yeah, if you're with the same angle and the same length, and the same acceleration.
So would you have the maximum mass ratio of this experiment?
We see that the maximum of the mass ratio should be conducted through our limitation on our laboratory scales, because well, I believe there is actually no maximum mass ratio for this experiment, but it's almost even possible to be done in a laboratory scale.
And you have mentioned the limit, and I want to know why is the limit?
Because while we're just for example, we're doing the mass ratio of 1 to 100. Just for example, it's actually very, very fast for the heavy load to drop, which actually means there's possibly no time for the light load to rotate over the rod and it just fall down. So it's also it has something to associate with the critical length for the motion and the phenomena.
And I want to know if this motion is in conservation of the energy.
Yes, we believe that, but there's a slight difference because we believe that friction would also consume some of the kinetical energy in this part.
So you think including what you say during
The friction.
essay,
The friction would
Oh, okay.
take up some of the energy.
if you included the friction in it, so that is energy conservation.
Yes, I suppose if you consider all the other systems.
As if you see the motion in energy conservation, so why don't you consider the air resistance of the light load?
Because we see like air resistance according to your model is like rather a light minor effect, because things like mostly would affect is actually the coiling of the rod, which causes the decay of the light load's action very, very fast. So we think it's actually the same as the mass of the cotton thread is actually negligible in this experiment. And as though we have conducted so many experiments regarding this phenomenon, so we also believe that it's pretty accurate to do so.
Okay, so what do you think? What keeps the heavy load from falling to the ground according to the problem statement?
Okay, so you mean explanation of the phenomenon, right?
Yes.
So
I want a brief explanation.
okay, so the very first part, the acceleration given by the gravitational force to the light zone actually forms a rotation around the rod, which gives us another centripetal force associating with the friction. So it gives the light zone a tension upward, which prevents it from falling. Okay, so while we release the light zone here, it's rotates around the rod, right?
Yes.
So there is a centripetal force.
Yes.
Which while you're rotating it on something, there's a force pulling it. So and next part is like why we actually deduce the Capstan equation, because we know that actually we don't have to let the centripetal force to be equal or even associated with the gravitational force to be equal to the gravitational force from the heavy load, because there are also friction associating inside this phenomenon. So actually while actually the phenomenon is while we're releasing it is forming a mechanical phenomenon that keeps the consistent of force which is in a range.
Okay, I understand. Could you turn to your friction equation?
Do you mean this one?
Yes. According to this equation, I consider that the friction is the constant.
Yes, it's constant if we have the same angle of coiling, because like while we're rotating this light load after one round, so that it will be like this one, then the friction will be different because we have another one round of thread. For example, if I can get this one here, so just for example, if we're using this as the cotton thread, so we're using it this way. So the friction would be absolutely different if we have like 2 more rounds on it, the friction will be different. So that's what we consider in our equation. Like with 2 more and 3 more, the friction will all be different with any single difference on the angle. So that is in one of the consideration of our experiment.
So would you consider the elastic?
Elasticity of the thread, right?
Yes.
So we've seen that in our experiment, it all exhibits a little bounce here, but we've deduced that actually, because since yes, compared as well to the coiling problem, it's actually just smaller and unresolved to a light load, because actually we examined the motion is actually very, very
Time is up for the discussion. The opponent summarizes 1 minute.
Yes. According to I just discussed with the reporter, he has mentioned that the strength mass can be ignored. I think the strength mass will cause a upward normal force, which can keep the heavy load from falling to the ground. And if there is no normal force, and the reporter's Capstan equation of the friction force can make sense, because the Capstan equation including the friction force and the normal force, and with the time passing by, the normal force will change. So.
Okay, thank you. The questions as a reviewer.
I think firstly want to affect the length, the difference of the length while every single round, right? Which is obvious, and it will slightly actually affect the geometry distance between the rod and the LISO, which may cause a little bit error in our experiment. I think this is very important.
How is the rod radius affected?
The rod radius. Oh. I'm sorry. If the rod grows getting bigger, and I think the area which is the area of the rod which getting contact with the string will getting more longer or bigger. So I think it will affect the friction force.
So, I see in your you measure the friction. I think it's not a connected friction. How is the
Oh, you mean the stopping part?
Yeah.
Oh, as well, we've like doing through the preliminary experiment, we've already calculated, but I'm not showing here because this is just for an example
yeah.
only.
So
So we can show it's like a threshold.
how do you think the friction will affect the whole
It was like, it will not affect in the general conditions, but it will slightly affect while we have two drawings.
So how do you think the connected friction Okay, how do you think if your string is flexible, very flexible?
That's very flexible. So actually, I mean, first part it will be like the bounce back of the heavy load is going to be very, very significant. So it will be actually give a very big experimental error in our graph, because since that every single part could be bounced back and actually.
Okay, so why the phenomenon will be observed?
I think we'll observe this case very, very steep, and it's going to be very, very steep as well.
So how do you think the string is very flexible?
The string is very flexible, and in your progress when you're releasing the LISO, I think the string will get curved or getting more affected by the air resistance.
Okay, so how do you think the string is very big? Big enough to affect the result?
I think it's not big because we measured that.
So how is it big?
Oh, it is big. So if it's big, we certainly have to consider it in our initial condition.
For the question. Reviewer, you have 2 minutes before the following discussion. Okay, the reviewer, please take the floor. 4 minutes.
So here's a problem statement. So I think the point is that we need to connect one heavy and one light, and we will split around the world and investigate the phenomenon. Okay, so for reporter process, we have a complete presentation and sufficient data, so we can extract phenomenon and the care survey is back. And concept is too fast here and time control and didn't compare the result to a series to a series and until set operation. And for opponent, she considered different parameters but she didn't follow reporter well and asked some simple questions and poor physics understanding. Okay, so they discussed will string mass affect the friction, and reporter answer is too small to negative, so it can negative, and we agreed with the reporter. Okay, and they asked for a max ratio of the mass ratio. Okay, the reporter answer there is no max, so and do the bigger as we can. Okay, so we agree to a reporter that it will have some different phenomenon when it is at a big mass ratio. Okay, and the air resistance and reporter answer is too small, so it can negative. And we agree to a reporter, but it may affect when they are in a small mass. And the ask for a two-step drop. The reporter answer like low rotating tension will hold the heavy one. So we agree to a reporter. Okay, and they discuss, and I asked them what if the spring mass is really big, and reporter answer they should consider a theory, and we think it will affect the tension, so maybe a theory should have some modification. And so I asked about what if the string is very flexible, and the reporter answer will have some oscillation, and we think it will oscillation too, and it will may affect the tension. And we asked for the connected energy to the reporter, and reporter answer they have to measure it. And we asked about the rod radius, will it affect the result? And reporter answer it may affect to the friction part and the geometry of the string, and we agree to a reporter, and it may cause some the light low fall when a high mass ratio.
Okay, thank you.
Okay, so firstly, thank you the opponent and reviewer us your constructive suggestions. So firstly, throughout the presentation, we mentioned that main focus on this phenomenon is associated with the gravitational force, the rotational action of the light load, and associating it with the friction. And through the discussion, we've discussed about like how the actual experimental error and potential in this phenomenon, and we've derive a lot of critical conditions which is involved in phenomena such as the mass ratio or the minimum mass ratio, and also the variable associated with the initial angle and the length, which believe that it could be dominant in how the phenomenon would differ from which we also observe the second drawing or even a third one. So we believe that actually this phenomenon is very interesting, while we can actually observe a different kind of phenomenon which differs a tiny bit as well according to the scale. So, well, thank you all guys for the discussion today. Thank you.
Thank you. Questions of the jury?
Yes, I have a couple of questions for the reporter. So first question is, what is the limitation of your theory?
What's the limitation of theory? So, well, the limitation of theory is actually you mean the frictional part or the whole theory?
No, for the whole theory, what's the limitation?
So, the first thing, the limitation is things that the complexity for the calculation. Well, we could actually draw all the forces actually working on line zone and heavy load, but with such complexity, we could actually only does this precise simulation to computers, which actually make us unable to calculate by hand.
No, I'm talking about. Do you think any other points that you did not consider in your suit?
Did not consider. Just as like the opponent and the reviewer has said, that this elasticity of the string and some other parameters would also affect, but we not consider that very thoroughly and comprehensively, and we're just like discussing the general mechanism for this graph.
Okay, so how do you verify the consistency between your theoretical prediction and experimental measurement?
Experimental measurement. So along with all the graphs we've given in our, so we've supported that, just for example, it's a little bit more. So we've like comparing the qualitative description on comparing to this kind of equations, but actually, as I said, it's very, very difficult for us to calculate. So we can actually cannot add a theoretical fitting line inside the graph for our comparison. So I think that is as well the limitation of our theory.
Okay, because you you have theory, so in principle you can predict something. For example, you have critical mass ratio, and then in principle you can do the experiment to verify.
Yes.
You have such kind of phenomenon. Okay,
Yes.
but of course here you did not show it. That's one thing. So, would you go to page 26?
26, yes.
Yeah, just a small question. 26. Why the initial point of your heavy load are different?
Heavy load are different. Because since like actually there's two loads so this is actually our fill on our display, and which we actually have done this in with defining those coordinates while simply, which is linear, but because like while we're analyzing this data, we put the wrong y position on it, so which caused a little bit different. I'm sorry about that. So both of them should be the same, and actually the absolute position of y of the y coordinates on the heavy load doesn't matter, because since that while in the vertical motion, the length of it actually does not matter about the tension and as well the gravitational force.
I mean, in principle, the initial point should be the same, right? Otherwise, I cannot compare the behavior of these two figures, right?
Oh yes, that is a problem that we should fix.
More questions?
I have a point for the review. You spent a lot of time to criticize a lot of math, something like that. Is that so important for this challenge?
First, I think the math is in the reporter theory neglect the air drag, the air resistance. But we think if there is a very, very small mass, so maybe the air resistance will affect a lot.
Okay, maybe for the opponent, I think you also spent quite a amount of time on asking about different errors that happen. The reporter just suggests most of them can be ignored. So what do you think about this phenomena? Is there a critical mass ratio for this phenomena to happen? No, just I'd like to hear your comment about this phenomenon.
You want the true value of the.
No, it's too heavy, of course, it will always go down. Is there a critical mass ratio between the heavy and the light mass?
Yes, I think it should be.
What is it?
Yeah, because I have done
4665. Any final comments for the break?
Because the reviewer, I think, you didn't play a very good role in this session, I think, because you didn't give the most of them very important comment, because you just said what's good, what's wrong, but you didn't mention it didn't fit the issue, okay? From the picture, from the formula, it just said what I think it did not match the issue, okay? Thank you.
Okay, thank you. If there's no more comments and ends the morning session. Thank all of you and see you guys afternoon.